Okay, so up until this point, we talked a little bit about centripetal forces, or got a brief introduction to those. We're going to dig a little bit deeper into that today, kind of break things down and find some good ways to get some calculations out of this in preparation for our lab. So if you guys remember from last class, we talked and spoke that any object that changes direction has to have an FNet, even if the speed isn't changing. So we talked about acceleration as being speeding up, slowing down, and changing direction. So is it possible to not be changing speed, but still have an acceleration? And the answer to that question is yes, it can be accelerating if it's changing directions. So when we talked about linear motion up until this point, we talked about, okay, well, we used our Suvat equations, and with our Suvat equations, we could figure out how to get from point A to point B. And now we're talking about rotational motion, which would be how to get from point A essentially back to point A again. And so the equations are going to be similar, but they are going to change a little bit, kind of depending on our needs or depending on what's actually going on in a given situation. So we have to be able to think critically about what's been presented to us in these given scenarios. And if we can do that, we can figure out some pretty neat and interesting things. So a couple of key terms that you're going to want to familiarize yourself with. I need to switch pens because that's purple, and I wrote the initial notes in purple. We're going to start with period. Okay, and let's just pretend for a second, and I drew it up here as well. So let's just pretend that we are looking at a record. For all of us hipsters, that would be vinyl, and it's got a radius R, and we're going to put a little bug on the end of that little radius. So he's not quite on the edge of the record, but he's pretty darn close. And we say that he's living here at point A. And we want to talk about this bug's motion. Well, if bug travels around on the record player, so we play the record and, bug just kind of catches a ride and doesn't move. And here he's going, and he's going ding, 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 all the way around the record. And he gets back to point A again. We can talk about that in two different ways. The first way that we can talk about it is as its period. So what was the bug's period? In other words, how much time did it take for him to go around one time? So that would be seconds per cycle. That's measured with a capital, or the variable that we use for that is a capital letter T. So that would be seconds per cycle. So let's say that it takes 1 second for this record to spin around to get back to point A again. That would make the bug's period 1 second. If we take the inverse of that, we wind up with the frequency. So if you guys look at the original period definition, that's seconds per cycle. So that's a measurement of time. T is measured in seconds. Frequency instead is cycles per second. So it's the flip of that. So if you notice, the variable there is kind of a lowercase f, and we say that that's equal to 1 over the period because that's just the inverse. Now, if we look at that frequency, looking at that as the inverse of time, you get kind of a weird unit that comes along with that. So cycles per second with frequency, in other words, how far did he get around in that 1 second? Well, in this particular case, if his period was 1, then his frequency would also be 1, because it would take 1 cycle per second and also 1 second per cycle. But if, for example, let's say the period was 2, in other words, that means it takes 2 seconds to go around one time, then the frequency of that would be 0.5. So in other words, you would get half a cycle for every one of those seconds. So if we have a period, a time T of 2 seconds, that means it would be 2 seconds for 1 revolution. So if we want to take a look at the frequency would be how many cycles for each second. Well, in that case, if it takes 2 seconds for 1, it would be a half of a cycle for just that 1 second. So that would be 0.5 seconds, or sorry, 0.5. We measure these things in hertz. That would be 0.5 cycles per second, or oscillations or revolutions, et cetera, et cetera. So because that's kind of a funky terminology, we pull out the crusty dead white guy. We give hertz as the unit that goes with that. That's a capital H and a lowercase z. So moving on, talking about angular displacement, this is the way that we measure how far displaced this bug gets from, say, for example, point A to point B. Why is it that we have to use the angle? Well, if we think about this, if we're looking at this in relationship to linear motion, point A to point B, you give, if we look at this with a certain distance, if we look at this as just displacement, we would have kind of this arc length of S, right? But let's say the bug wasn't sitting quite in this location. Let's say the bug was sitting a lot closer to the center. Well, that point between point A and point B is going to be a lot shorter. So that actual linear displacement doesn't quite match up. So when we did linear, displacement was measured from a fixed reference point, but because circular is moving and because we're in different locations, we're measuring it as the angle, because the only thing that stays the same between point A and point B, regardless of where the bug is, and now notice the radius changes as well, because you bring them in closer, but that angle is pretty consistent through that entire measurement. So we say that it's the angle through which a rigid object has rotated from a fixed reference point. Now here's where things get a little bit sticky. You got to bring in some of your Algebra 2 mad skills, because this angle is not measured in degrees, it is measured in radians. So our friend the radian, we say it is a better way to circle, if you will. Radians are basically an angle that's expressed in radians is a ratio between the arc length and the radius. So if you guys remember learning in your math classes, hopefully fingers crossed, that 360 degrees is kind of an arbitrary designation. So saying that, you know, that one circle has a total of 360 degrees in that circle was brought about by the Mesopotamians. Some people say the Babylonians. Who knows? It was ancient. It has something to do with the fact that like 6 triangles fit perfectly in there or something. And so they liked that kind of base 6 system. 360 was a nice number. So we said, all right, we're going to call a circle 360 degrees. And it really does work out quite nicely. But when we want to talk about things in terms of physics, the radian is a much better way to do it. Just because it helps us again to account for that consistency with being the angle that gets passed through, as being that fixed reference. So the theta that is in any of these measurements is actually measured in radians, and that's a relationship between S over R. So S being displacement, and looking at that, we know that that would be basically that arc length. So it's a ratio between arc length, S, and radius, R. So if we look at what that basically breaks down to, if we talk about S, or if we talk about a full circular movement about a circle, we know the formula circumference is 2 pi r. So if we say, for example, we're going to take a circle, let me get a different piece of paper here. So let's say we're going to get a circle. It's got a radius r, and we're going to rotate it through this arc length of S all the way to here. Well, this here is also r. We have this angle that gets measured out, and this arc length S is that distance. So we sort of take this as a ratio between what that arc length is and how well it relates back to this, how well it relates back to this radius. So if we wanted to take the full circumference, you guys remember from geometry, circumference is equal to 2 pi r. So that basically means that that would also be equal to 360 degrees, right? Because that would be a 360 degree trip. And so if we take a look at how that kind of cancels out, we can say that 360 degrees is going to be equal to 2 pi radians. So in other words, you get, as you make this trip all the way around, it's the value, or this distance, is going to be 2 pi. Okay, so if that's 2 pi, then 180 is going to just be pi radians, right? So like I said here, 180 is pi radians. So the conversions are just a matter of setting up as a ratio. So in other words, if we want to take 60 degrees and convert it to radians, we would start with our 60 degrees. We would multiply it by pi over 180 because pi is 180, and that would give us pi over 3 radians. And there you have it. So that would be our answer. It would be pi over 3 radians for 60 degrees. Now, if you have, so if we want to take a look at this and we want to know what 1 radian is, going by the same process, 1 radian is actually equal to about 57.3 degrees. So in other words, we take that value again, we take 1 radian, we set that equal to 360 degrees is 2 pi radians, and that gives us, as we kind of hammer that out, that's 360 divided by 2 pi, it's about 57.3. So at the bottom, you have a couple of practice examples. You should probably take a second to do those practice examples and then check your work when we come back for the next part. It's just a couple quick conversions, converting 137 degrees to radians. So again, taking 137, multiplying it by pi over 80, you get your answer in radians, you get on with your life. Same thing with how many degrees in radians does a rotating object pass through 5 revolutions? We'll take a look at that as well. And then number 3 might require a little bit explanation, but we'll get to that in a minute. So just try those on your own and then move on to the next video.